Hi there, Mr. Sutton with the AB Calculus 614 homework solutions on volume with known cross-sections. For this problem, we have a base of a solid enclosed by a semicircle and the x-axis, and cross-sections with respect to the x-axis are perpendicular to the x-axis are rectangles, heights twice that of the side in the xy plane. So we'll start this by figuring out the area of the cross-sections in terms of x. Our area in general, a of x, is going to be base times height, but we need to have only one variable. Let's express this in terms of the base first, and then we'll talk about the x's. So they said the heights are twice that of the side in the xy plane. Well, they're basically saying the height is twice the base. So this is b times 2b, which is just 2b squared. All right, so what is b? Well, b is going to be the distance between your function and the x-axis. So that's going to be just the square root of 49 minus x squared, because it would be this minus 0, so it's just this. So we have 2 times the square root of all this squared. Now for the limits of integration, this semicircle and the x-axis equal each other when x is positive or negative 7, we can see here, or you could do it more algebraically. So then we have the integral for volume. We have the integral from negative to positive 7 of this area formula here. And now the rest happens on the calculator. So on Desmos here, let me enter in my a of x function. So a of x equals, we got 2 parentheses, and we've got square root 49 minus x squared. And I realize that after I square this, that square root's going to go away, but whatever. No need to really simplify if I don't have to. And then let me do my integral from negative 7 to 7 of a of x dx. Comes out to 914.667, roughly. So there we go. For this problem, we have the base of the solid as a region enclosed by this upside-down parabola and y equals 0. Cross-sections are isosceles right triangles with one leg in the xy plane. So let's get our area formula to start off with here. So let's just think this through. If we have an isosceles right triangle, that means 2 legs are the same. One leg is in the plane. Now the right angle in an isosceles right triangle is between the 2 legs, because the third side across from the right angle is the hypotenuse, not the leg. So that means we have one leg down here, one leg sticking straight up here. So we have basically a base and a height for our triangle with these 2 legs. So my area formula in general, 1/2 base times height. But because this is an isosceles triangle, the base and the height end up being the same exact thing. And the key here is that one of the legs is already in the xy plane, so you know the other leg has to be the height. So I'm going to write this as 1/2 base squared in this case. Now what is the base? Well, that's just going to be the distance strip between my bounding functions, which in this case is just this parabola right here. So we have 1/2 times all this craziness squared. That's our area formula. And now for the limits of integration, we need to set this stuff equal to 0. And if we do a little bit of algebra here, let me see. I'm just going to multiply everything by, let's just multiply everything by negative 4. So that would be x squared minus 16 equals 0. Add the 16 and square root it. We have x is going to be plus or minus 4. So for my volume, I have the integral from negative to positive 4 of this area formula with a little dx after it. And now it's time for some calculator action. So entering this on Desmos, let me do my a of x function first. So that is, let's see here, 1/2, and then open a parentheses. We've got, other way. We've got negative fraction x squared over 4 plus 4, close parentheses, raise it to the second power. And now let me do my integral from negative 4 to 4 of a of x dx, and that comes out to 34.133. For this problem, base of a solid is the region enclosed by this semicircle and the x-axis. Cross-sections are isosceles right triangles with one leg in the base. So here's just a 3D representation of this, just because I can. So there's my semicircle. Here's my isosceles right triangles with one leg in the base. We're going to start by getting the area of the cross-section, this triangle area, in terms of x. That's going to be a of x equals 1/2 base times height in general. But now since this is a right isosceles triangle, here's your right angle here, that means that this leg and this leg are the same distance, so the base and the height are actually the same thing. So this is then going to be 1/2 base times base, or 1/2 base squared. And what is the base? Well, it's just the distance between the semicircle and the x-axis. So that's just going to be 1/2 times the square root of 9 minus x squared, all that squared. Now I need my limits of integration. So that's where my semicircle equals 0. And even if we didn't have the graph here, we can see that if I plug in 3 or -3, that's going to zero this out. So my volume then will be the integral from -3 to +3 of this a of x I just wrote out. And now I need the calculator. So let's do all this on Desmos now. We've got a of x equaling 1/2 parentheses square root 9 minus x squared, and then we'll close that and square it. And yeah, the square and the square root cancel, but again, no need to simplify if we don't have to. And then let's just do integral -3 to 3 of a of x dx, and that comes out to exactly 18. Nice. On this problem, we're told the base of a solid is the region enclosed by this semicircle here and the x-axis. Cross sections are semicircles. So here's a picture of what's going on here. We have a base, the area that's a semicircle, but we also have cross sections that are semicircles. So somebody really likes semicircles, whoever made this problem. Let's start by getting the area of these semicircle cross sections. So for that, I'm going to use the general formula a of x equals 1/2 pi r squared over 2, or 1/2 pi r squared. The radius, though, you've got to be careful here. So normally, the thing that you plug in for your area formula variable is the distance between your two bounding functions. In this case, though, this formula uses a radius, not an outright base. The radius is just half the distance across this semicircle cross section here. So in this case, we're not doing square root of 16 minus x squared. We're doing all of this divided by 2 for the radius. So I'm going to write this as 1/2 pi times, and I guess I could say 1/2 radical 16 minus x squared. And that inside piece is being squared. Well, actually, everything in here is being squared. This divided by 2, that whole thing is the radius, so the 1/2 gets squared as well, and that's an important point here. All right, let me find my limits of integration. I'll set my semicircle equal to 0, and I'm going to get plus or minus 4 if I do all the algebra on this. So I need the volume then from negative to positive 4, so integral from negative to positive 4 of my a of x formula. And now let me just carefully put this in the calculator. So we'll go into Desmos to enter this in. Let's see here. We've got a of x equals 1/2 pi, and then open a parentheses, 1/2 in there, and then square root, sqrt, 16 minus x squared. And then I'll close that parentheses and raise that to the second power, and all of that's a of x. Let's bring this up now so I can see what I'm actually entering. So I need to do integral from -4 to 4 of a of x dx, and that's about 33.510. On this problem, they're telling us that R is the region in the first quadrant bounded above by the graph of y equals ln of 3 minus x for 0 to 2. And then they're telling us this is the base of a solid with cross sections that are squares, perpendicular to the x-axis. So what's the volume of this thing? So just as a 3D model of this thing, if you wanted it, here's what's going on. We've got this ln function being graphed out, and we've got some squares popping out of that. All right, so let's start by getting the area of the cross section. So those are squares. We can just write a of x equals s squared, but we need to express this in terms of x so that we can actually integrate it. So the side of the square, the base of the square, which is also the height, that's just going to be the distance from the x-axis to the ln function. So I'm just going to put in ln of 3 minus x, that whole thing squared. So ln squared of 3 minus x, I guess you could write it as. And then we already have the limits of integration. They gave that to us, 0 to 2. And you can see here that we're crossing the x-axis at 2 if you were to graph this out on a normal graphing calculator. Yours, unfortunately, does not do 3D models. So we have the integral then from 0 to 2 of my a of x function I just wrote, dx. And now I have to do it on the calculator.
So here's my Desmos. Let me do a of x equals, and we'll define that as ln exponent squared, and then 3 minus x. And then let's come down here and do my integral. So integral 0 to 2 a of x dx comes out to about 1.029. And that is going to match answer choice B.
For this problem, the base of a solid is the region enclosed by this curve here, and they're actually showing us that in the figure. So it's kind of like an ellipse, but it's a little bit flatter at the ends. So anyway, for the solid, each cross-section perpendicular to the x-axis is a semicircle. What's the volume? Okay, so we have to start with our area formula for the cross-section, semicircles, so we can write a of x equals 1/2 pi r squared. But getting the r is a little bit trickier on this one. So the r is going to be half the distance from one end of our solid's area to the other. So we have to first get this in terms of y, because if we're talking about distance from the x-axis or just up-down distance, we need y equals. So let's rearrange this formula a little bit. I'll start by subtracting x to the 4th over 16 from both sides. And then I have to multiply everything by 81. I'm going to do that, and I'm just going to leave all this in a parentheses next to the 81. Then I need the 4th root of everything. And since I'm taking the 4th root of an equation, I need to do a plus or minus. It's an even root, so I need a plus or minus. So when the dust settles, I've got plus or minus 4th root of 81 times 1 minus x to the 4th over 16. So a whole bunch of algebra happening there. And now I'm going to use this to figure out my radius. So down here I've got a 1/2 times pi times 1/2. And now I'm just going to take half of the distance from here down to here. The top curve is given by positive all this stuff. The bottom curve is given by negative all this stuff. So I've basically got one of these radicals plus itself inside here. And once I take half of this radical plus itself, I square that, and that gives me my radius squared. So this is kind of gnarly to enter in the calculator if you're not being a little bit clever about it. So let me show you in a minute what that looks like. Before we do that, though, limits of integration on this one. Well, we can see from the picture we're going from -2 to +2. So let's go with that. So our volume then, we have the integral from -2 to +2 of, well, I really don't feel like rewriting all of this. So I'm just going to write a of x dx. Now I have to do some work on the calculator.
So here I am on Desmos. This is a bit of a mess to enter even with this graphing utility, but let's give it a shot. So this whole 4th root craziness, I'm just going to give that its own function. I'm just going to call this f of x, just so I don't have to keep rewriting it. And this is going to be 4th root, so I need to use nth root in Desmos. And then I'll put a 4 up there. And inside I've got 81 parentheses 1 minus x to the 4th divided by 16, and we can close that out. And now let me write my a of x function. So that's going to be 1/2 pi, and then I'm going to have a parentheses, this brackets parentheses that's being squared. I'm going to write that first so I don't lose track of that. And then inside we've basically got 1/2 times another parentheses, big parentheses. I'll put that in there. And that's really just f of x plus f of x going on, so I'm just going to write 2f of x. And that should hopefully be my a of x function faithfully reproduced. You could write the whole thing out, but it's definitely a mess. So let me do my integral now from -2 to 2 of a of x dx, and this is a -2 down there, and that comes out to 49.425. Does that match an answer choice? It sure does. Answer choice E.
For this no calculator problem, we're given the base of a solid is a region bounded by the x-axis and this graph, which is a semicircle. For the solid, each cross-section is a square, and this is perpendicular to the x-axis. We want the volume of the solid. So here's a 3D representation of the situation. So we have some semicircle with some squares coming out of it, and this isn't the exact semicircle that they gave us up here, but it'll do for visualizing this. So we need the area of the cross sections, and then we're just going to integrate that across the interval without a calculator. So I'll start with a of x equals s squared because we have squares for cross sections. The side of the square is just going to be the distance between the x-axis and this graph, which is just the square root of 1 minus x squared. And we're squaring all that. Now, because I'm doing this without a calculator, I am actually going to get rid of the radical by squaring it. So I have 1 minus x squared is my actual area formula that I'm going to be using. Now, before I can set up an integral with this, I need to find my limits of integration. That's going to be whatever makes this square root function equals 0 because it's intersecting the x-axis. Those are the bounding curves. So let's see here. We could do a little bit of algebra, square both sides, subtract 1, divide by -1, square root. Eventually you end up with plus or minus 1 for your limits of integration. So now we're going to take the volume by doing the integral from -1 to 1 of this area formula here, 1 minus x squared dx. And we're just going to go step by step and integrate this. So for my antiderivative, I've got x instead of 1. Minus, this is going to be 1/3 x cubed. We're going from -1 to 1. So I have all of this stuff with 1 plugged in, minus all this stuff with -1 plugged in. For this first brackets here, I essentially have 1 minus 1/3, which is 2/3. Over here, I have -1, and this is actually 4 negatives altogether. So this is going to be plus 1/3. So we're doing -2/3 in here. But we're subtracting -2/3, so that's positive 2/3. Again, no calculator, so you had to be careful with this, and that adds up to 4/3, which gives us answer choice B.
For this calculator-based area and volume problem, we have f and g, functions given by 1 plus sine of 2x and e to the x over 2, and then r in this diagram is the shaded region between those two in the first quadrant. So for the first thing they want us to do, it's to find the area of R. Okay, well, it would be helpful to have f and g entered in my calculator, so let me go ahead and do that. So we've got f of x equals 1 plus sine of 2x. There's one thing. And then we have g of x equals e exponent x over 2. So there's another one. So this is the region that they're talking about here in the first quadrant if we just zoom in a little bit there. All right, now to find this area, we need to take an integral of basically top function minus bottom function, a bunch of little distance strips. And we need limits of integration. So we need to know where these two functions equal each other in this area. There might be other places, but we don't really care about them. So I'm going to write f of x equals g of x, and then let me find this on my calculator. So I'll just click on one of the functions and I'll bring this up so I can see it. So we have a spot here that's actually at 0, which is good. And we have this other x value as well at about 1.135 and some change. I'm going to need that value, so I'm going to actually copy that. And I'm just going to call that k, or whatever letter you like. And now I can just reuse that whenever I need to. So I'm going to say these equal each other at x equals 0, and at x equals, again, I'm naming this, k equals that value there. So now I need the integral from 0 to k of top function minus bottom function, and they labeled them for us. It was very nice the way they set this up. So we can just write f of x minus g of x in a parentheses dx, and then just plug that in the calculator. So going back here, let me just move this a little so I can see. So we have integral int from 0 to k, parentheses, f of x minus g of x, close parentheses, dx, and that's about 0.429. Now in this problem there was no units whatsoever, so we don't need to give them in units, and this one is just done. For part B of this problem, they want us to find the volume of the solid generated when R is revolved around the x-axis. Okay, so we're taking this region, revolving it around the x-axis to get some solid of revolution. That means we're going to need to come up with the cross sections for this. And if I have to choose between disks and washers, since there's a space between the region that's bounded here and the axis of revolution, we're going to need washers for this. So I'm going to use pi times big R squared minus little r squared. Now I'm going to call this a sub 1 of x. Normally I wouldn't bother with the subscript, but I kind of looked ahead and I know in part C that I'm going to need another area formula that I don't want to mix up with this one. You never want to assign the same function name to two different things in the same free response problem. It gets very confusing. So this is my my area function for this part of the problem. And again, we're using washers. So for my big R, that is the distance from the outer part of the bounded region to the axis of revolution. That's just f of x out there. And then for little r, that's this inner distance between g of x and the axis of revolution. So we've got minus g of x squared. And now I just need to plug all this into my calculator. I'm going to be doing the integral again from 0 to k of, and now I'm going to use a sub 1 of x dx. All right, so back on the calculator, I can get rid of that little thing there. Let me write my area function, a of x, and I'm not going to bother with the subscript here. And then we've got, this will be pi, parentheses, and we had f of x, close that parentheses and square that, minus, parentheses, g of x, close that parentheses and square it. So I've got my area function, and now I need the integral. And let me scroll down here. Integral from 0 to k of a of x dx, and that comes out to about 4.267. For this last part of the problem, they're telling us the region R is the base of a solid. For this solid, cross sections perpendicular to the x-axis are semicircles, with diameters extending from f of x to g of x. We want the volume of this solid. So visually, imagine we have a bunch of semicircles whose diameter is this distance here, and these semicircles are just kind of popping right in your face out of the page at you here, and that forms a solid. So we just need to find an area formula in terms of x for these semicircles, and then we can just integrate that from 0 to k, just like we've been doing everything else. So for my area, since we're dealing with semicircles, the area of a whole circle would be pi r squared, so we need 1/2 pi r squared. I'm going to call this a sub 2 of x equals 1/2 pi r squared. And the only thing we really need to kind of fill in and put in terms of x is this radius. Now we do need to be careful. It's tempting to just say f of x minus g of x for the radius, but that's actually the diameter of these semicircles. If we want the radius, we need to take half of f of x minus g of x. So for my r, I'm going to write f of x minus g of x over 2, and I'm going to put that whole f of x minus g of x over 2 business where r used to be. So this is my area formula this time around. And just like before, I'm going to be integrating this from 0 to k, and this time I'll have a sub 2 of x dx. And let me just go back to the calculator now. I can leave this a of x dx where it is because I'm not changing that. I am going to change this area formula though. So let me just get rid of all of that. So this is going to be 1/2 times pi, and then parentheses, fraction, f of x minus g of x, all of that over 2. Close the fraction. And that whole fraction, that whole parentheses here, we see this needs to be squared. So we'll put a square up there. Square that. And now if I look down here at my integral from 0 to k of a of x d of x, it's already in there. That seems kind of small, but it comes out to 0.078 when the dust settles.